We now turn to analyze the basis pursuit algorithm in the presence of noise. Our goal is to prove that its result is stable, namely not being too far from the original sparse representation that generated the given signal. As before, we start with an S-sparse vector x0 and create B from it by A times x0 plus noise. We assume that the noise is of bounded norm epsilon. Given A, B, and epsilon, our goal now is to approximate the solution of P0 epsilon using the basis pursuit. This means that we will be solving this minimization in which L1 has replaced the L0. The solution is x hat, and as x0, it obviously satisfies the epsilon constraint. Thus, as before, the L2 distance between Ax hat and Ax0 is upper bounded by 2 epsilon. Let's define the difference x hat minus x0 as d. So far, the analysis seems to resemble the one we had for the P0 epsilon stability, but now comes the difference. We do not know that the vector d is sparse, and thus we cannot invoke the RIP. So how should we proceed? As we are about to see, the answer is given by the L1 measure that the basis pursuit optimizes. So far we saw that the squared norm of A times d is upper bounded by 4 times epsilon squared. Now we open the L2 expression and break it into two parts, the squared L2 of the vector d plus another quadratic term in which A transpose A minus the identity serves as the weight matrix. Observe that this is the Gram matrix we are familiar with, minus its main diagonal that contains only ones. The next step is to replace the second term by an upper bound on it that takes the absolute of the elements in this term. Due to the negative sign, this upper bound turns into a lower one for the overall relation. As our last step, we replace the absolute of A transpose A minus the identity by a matrix that has zeros on the main diagonal and mu, the coherence, everywhere else. Observe how we write this as a column vector of 1s multiplying a row vector of 1s minus the identity, and all this is multiplying mu. Since we have increased the entries in the matrix, the overall expression is smaller and thus serves as a lower bound. This is what we have obtained so far, and we can open now the parenthesis in the rightmost term. This leads to an additional squared L2 norm of d multiplied by mu minus mu times the square of the L1 norm of d. This L1 norm came from the multiplication of the absolute of d times a vector of 1s. Our way to proceed returns to the fact that x hat was obtained as a solver for the basis pursuit. This means that its L1 norm is necessarily no larger than that of x0. We will turn this inequality into a more comfortable expression in a way that should remind you of something we have already done. Remember that d is defined as x hat minus x0. Thus, this L1 inequality can be written alternatively as this relation in which we replace x hat by d plus x0. These two L1 expressions can be described as two sums, one over the support of x0 and the other over the rest of the elements in which x0 is simply 0. We simplify the first of the two by exploiting the reverse triangle inequality. The elegance in the outcome is the fact that x0 does no longer appear in this expression. We add and subtract the sum over the support and get to this final outcome that states that the L1 norm of d is upper bounded by twice the sum of the absolute entries of d over the support of x0. We shall take this outcome and return to our earlier derivation. These are the two inequalities we obtained so far, and now we shall take the second and plug it into the first. Since we have an upper bound on the L1 norm of d, and since its sign in our first expression is negative, we can further bound this term from below as shown here. Our next step is a bit delicate. The sum of the S on support elements from the absolute of the vector d could be considered as a sort of an L1 norm over an S-long vector. We do know that for any vector of length s, its L1 norm can be upper bounded by its L2 norm times the square root of its length, s. This statement is part of a much wider property of norms, claiming that all norms are equivalent, and every norm can be upper and lower bounded by another, with proper non-trivial constants. Using this, we get to the following expression, and our very last step is to replace the limited summation over s elements with a summation over the full vector D, thus getting an L2 norm of D in the rightmost term as well. Believe it or not, that's it. If the coefficient multiplying the squared norm of D is positive, we can divide by it and get a bound on the length of D, which is nothing but the stability we so much desire. Here is a theorem to summarize our findings. The coefficient we required to be positive poses a limit on S, and subject to this condition, we get that the basis pursuit result, x hat, is not far from x naught, being bounded from above by 4 epsilon squared divided by an expression that depends on mu and s. Several comments are in order. First, when epsilon is 0, we return to the noiseless case, for which D is simply 0, suggesting that x hat and x naught are the same. However, we see that the permitted cardinalities to enable this result are more restricted, a fact that testifies that our proof is not tight. As in all other proofs of stability and equivalence, this result is a worst-case one, and better results could be envisioned. Indeed, one can prove that basis pursuit leads to a near-oracle performance if the noise is assumed to be random. In this case, the stability error is the oracle's one, up to a constant and a log factor.